Welcome to our notes on financial applications. Students will be able to model and solve financial application problems using exponential functions. So here we're going to focus on the compound interest formula, where B is the ending balance in dollars, P is the principal balance, which is the starting or the original balance, the initial balance, or investment in dollars. R is the annual percentage rate. We call that APR. We've probably heard that a lot in a lot of commercials. And it's always expressed as a decimal. So you always have to turn the percent into a decimal. N is the number of times interest is compounded annually, so within 1 year. And T is the number of years. T will always be in years. T will never be in months. Or days or anything else. So if it asks you how much money will be in the account in 6 months, you have to convert that to 0.5 years instead. So here's some key vocabulary that we should probably know. A savings account is an account in which the bank pays you interest for the use of your money deposited into the account. And forgive me, I do not know how to pronounce this author's name, but he is the author of a financial algebra textbook. And so just be mindful, most banks do not give you a super large percent interest. So be mindful that the problems that we're working with probably have much higher interest rates than what real banks use, because ultimately banks don't really want to pay you. They would much rather, loan you money so then they can charge you a large, interest so that you pay them for the use of their money. So that's just kind of how things go. I highly recommend that you take a personal finance class if you have the ability to do so. Also, we should know what compound interest is. It's money earned on the money deposited plus the previous interest, also by the same author. And there are different types of compounding. They are as follows. So if the interest rate is compounded annually or compounded once a year, or if you see that the APR is this, the end value in the formula is going to be 1. It only happens once a year. Semi-annually means every 6 months or twice a year. So if the interest is compounding semi-annually or twice a year, then that means the end value is 2. Okay, I think you can see the pattern that's going on here. If it's compounded quarterly, every 3 months, that means it happens 4 times in 1 year. Monthly, there are 12 months in a year, so it happens 12 times in a year. Weekly, about 52, as there are 52 weeks in a year. And daily, we're just going to go ahead and assume 365, but of course on a leap year, we would use 366. And I'm not sure if a lot of people decide to use 365.25 to accommodate, but that's okay. For the most part, we're going to use 365 every time we say daily. And continuously means that it compounds infinitely many times, which is a really difficult concept to explain. But it goes by a completely different formula. See, here now we got to use this E. Okay, so we don't use this formula up here when something is compounded continuously. We use a completely different formula and it follows that. All right, so let's go ahead and look at an example. It says Sam makes an initial investment of $8,000 for a period of 5 years. Find the value of the investment after the 5 years if the investment earns the return of 3% compounded monthly. So, what's given? That $8,000 is the principal. That's the initial amount that Sam is going to put into the investment. Okay, so initial is the P value here. Let's see, what else are we given? A period of 5 years. That means we were given the time. Time T equals 5. And also we're given the 3%. Okay, the 3% has to be converted into a decimal. This is how we do it. We take the number and we divide it by 100. Percent means out of 100. So 3 out of 100 is 0.03. And we're also told that it's compounded monthly, so that means the end value is 12. So what do we need to find? We need to find the B value. Okay, that's how much we want to know how much his balance is after 5 years. Okay, so what do we need? We need this formula. So I went ahead and copied it here. And I'm just going to go ahead and replace everything that we know and then use my calculator to solve. And so his ending balance is $9,292.93. Now in their calculator, you're going to have a lot of decimal places, but because it's money, you're going to round to the nearest cent. Okay, so only 2 decimal places. All right, so now the question is, how long will it take for Sam's investment to double? So what's given? We know that his principal amount was $8,000. That's his initial investment. We also know that the percentage is 3%. So we're going to leave that in decimal form. And we know that it's compounded monthly, so N is 12. And now we know that his ending balance will be 16,000. Okay, so all I did was double 8,000 and I got 16,000. And we are being asked to find the time. It says, how long will it take? That means we don't know the time. And so that's what we have to find. So what do we need? We need this formula. We're going to plug in everything that we know. And so notice that t is in the exponent position. How do I get this out of the exponent? Well, there's only one function that will allow me to do that, and that's going to be logarithms. But before that, I have to get rid of this 8,000. So I'm going to divide both sides by 8,000 to get this. Now I can go ahead and take the log of both sides. You can use the natural log here. You can use the log. If your calculator can do any log base, that's cool, but I'm going to pretend like I only have access to a scientific calculator that does not have that. So I'm going to take the log of both sides. Okay, and then I'm going to use the power rule of logarithms to bring the 12t down as a coefficient. Okay, now this is just a number. It looks gross, but it's a number. And this is a number, and everything is being multiplied here. So really, if I'm trying to get t by itself, I'm going to divide everything by this 12 times that log. Okay, so t is this expression here that now once I put into my calculator, I will get the final answer. It will take about 23 years for Sam's investment to double. And here I just use 3 decimal places because it does make it more accurate. If you would like to test the difference between using just 1 decimal place versus 2 versus 3, you'll find that using 3 will get you even closer to 16,000. Okay, so why don't you pause the video and try to figure out how long it will take for Sam's investment to triple. Okay, how long will it take for Sam's investment to triple? Go ahead, pause it, try it on your own, get to a final answer, and then start the video again, and I will show you how long it takes. Okay, so this is almost identical to the last problem in which we asked how long will it take for Sam's investment to double. The only difference now is that I'm tripling his initial investment. Okay, so I'm just going to go ahead and put all of the given things there. This is the only difference. Instead of multiplying 8,000 by 2, I'm multiplying it by 3 because triple. Okay, so I get 24,000 for my B value, and I'm still asked to find the T value. So what do we need? We need that formula, of course, and we're going to plug everything in that we know. Okay, now I got to get this expression, this part, this factor by itself. So I'm going to divide both sides by 8,000, and I'm left with 3 on this side. Okay, and then I'm going to take the log of both sides so that I can get this exponent down. Logarithms are the only things that can bring a variable or something down from the exponent. So I'll do that. I'll divide everything, and I'll get my t-value as such. Okay, so remember, this is just a number, and it's being multiplied by 12. So to get t by itself, I'm going to divide both sides by that. Okay, when you plug this into your calculator, you're going to get about 36.7 years. Okay, and again, I'm just using 3 decimal places because it is more accurate. But yeah, this is how we figure out how long it will take for Sam's investment to triple. All right, so financial applications are not the only type of applications for exponentials. Let's look at a few more. So students will be able to model and solve application problems using exponential functions. So here's an exponential equation, y equals a times b to the x, where a is the initial value and b is the growth factor or the decay factor. It also has other names like common ratio, multiplier, etc., etc. Okay, when the a value is positive and the b value is greater than 1, you will have growth. Okay, when the b value is greater than 1, we call it a growth factor. You'll have decay if the a value is positive and b is between 0 and 1. Okay, it can also look like this because of our exponent rules. So what does this mean? This means like numbers like 1/2, for example, is going to represent a decay exponential function. Okay, we also have this form here in which r is a rate in decimal form. So it's going to be given to us in the problem as a percent, but we must put it in as a decimal form. It's very similar to our financial application that we saw previously. So you'll have growth if you see something like increases at a rate of r%. So then you use the plus inside. Okay. If you see decreases at a rate of r%, then you will use the minus inside. So let's go ahead and do an example. It says during normal breathing, about 12% of the air in the lungs is replaced after one breath. Write a model that calculates how much original air is left in the lungs if the initial amount of air is 500 milliliters. How much of the original air is present after 240 breaths? Okay, so let's start with what's given. Okay, we know that we have a percent in here. 12% has to be converted to decimal form, so I went ahead and did that. Now, the word replaced, like replaced after one breath, is hinting at decay. So this is not growing, right? The original amount of air is leaving our lungs every time we breathe. So 12% of the original air that we breathe is exiting our lungs. So decay is what we're going to need. And also, we're told that the initial amount of air is 500 milliliters, okay? So there's two things to find. The first thing was to find an equation that represents the problem. It says write a model that calculates how much original air is left in the lungs if blah, blah, blah. So we're going to write an equation that represents the problem. So sometimes rewriting or reframing the question can help you find it. So if I say x is the number of breaths, and f of x is the amount of original air left in the lungs in milliliters, then this is the formula that I'm going to put together, okay? Where this is the a value, and this is 1 minus r. So remember, we had to determine if it was going to be growth or decay because we needed to know if that was going to be a plus or a minus. In this case, it's a minus. Okay, so if I go ahead and simplify, you see that 0.88. Now it's in this form up here. Now it's been re-expressed as that form there. And notice that the b value is between 0 and 1, and that means decay. So we're actually on the right track. So I will accept either one of these, but it's probably a lot nicer to look at this one. Okay, so that was the first thing. We wrote an equation to represent the problem. And the second thing we have to find is how much original air is present after 240 breaths. What is that asking me to do? It's asking me to plug in 240 into the function that I just created. So if you go ahead and do that, okay, and put this in your calculator, you'll see something like that. So how do you read that? This e negative 11 is telling you this is the exponent on 10. So it's giving you scientific notation. So is this number times 10 to the negative 11. That's how we interpret that. So that's how I would write it. This is how you can abbreviate milliliters, okay? M capital L, okay? L is for the liters. Milli, the small m is for milli. Okay, so you can write it out like this, or you can write milliliters like that. Okay, so here are some more exponential applications and some keywords and what they mean. Half-life, or something that decays by half. The base is going to be 1/2, okay? That's the number we're going to be multiplying the original value by each time. We're going to be multiplying by half if something keeps decaying by half. If something is doubling, then that means the base is going to be 2. If something is tripling, the base will be 3. And if something is quadrupling, the base will be 4. So I think you kind of understand what's going on here. The words will help you determine what the base is. So let's go ahead and try this example. The half-life of palladium 100 is 4 days. After 14 days, a sample of palladium 100 has been reduced to a mass of 8 milligrams. Part A says, what was the initial mass in milligrams of the sample? And part B says, what is the mass 6 weeks after the start? Okay, so what is given? We know that the half-life is 4 days. That means that's how long it takes for half of what you have to be left. Okay, so that means the base of your equation is going to be 1/2. And we know that after 14 days, you'll only have 8 milligrams left. Okay, so let's first try to understand this problem of half-life. How do we even put together an equation? We're going to need that because we have to find the initial mass. So let's try to understand it. I'm going to make a table here. I'm going to go all the way up to 8 here. So let's say, and I'm going to make this up, let's say that our initial amount is 100 milligrams. Okay, if my initial amount is 100 milligrams, then after 4 days, I should be left with 50, right? Because I'm going to do 100 times half to get 50. And then that means another 4 days, I'm going to end up with half of that. So how do I write a function where I'm skipping by 4th each time? Okay, so I think it's safe to say that I know I'm going to have this situation happening because if I made my initial value 100, it will go here. This is what I'm going to be multiplying the 100 by to get to the 50. So that means this exponent has to be 1 for this 50, but how do I plug in x? How do I plug in x equals 4 to get an exponent of 1? So I think what's useful is for me to write x divided by 4. Okay, because now if I plug in 4 in here, I'm going to get 4 divided by 4 in the exponent. That's 1. That leaves me with the 50 here. 100 times 1/2 will be 50. And let's just double check. If I were to plug 8 in here, 8 divided by 4 is 2. So 100 times 1/2 times 1/2 will in fact give me the 25. So this is the formula that I will use, okay, if my initial value was 100. But notice we don't actually know what our initial mass is, so we have to find it. All right, so now let's come back to the problem. What do we want to find? We want to find the initial mass, okay? So let's put together the function to the best of our ability with what we know. So if I use function notation, I'm going to call it f of x. You can call it whatever you want. Equals a. I don't know what the a value is, so I'm going to leave it. That's actually what I want to find. I want to find what is a. Okay, But I do know that there's a half-life of 4 days. That means the base is going to be 1/2, and my exponent is going to be x divided by 4, okay, where this value down here in the denominator is how long it takes for something to decay by half. Okay, that's this information right here. So now that I have that, another piece of information that I know is that after 14 days, I have 8 milligrams. So what I'm going to do, actually, let me just go ahead and define my variables. This x is going to represent the number of days, and f of x is going to represent the amount of palladium 100 in milligrams after x days. Okay, so the amount in milligrams of palladium 100. Okay, so now that I've defined my variables, I'm going to go ahead and plug in the information that I know. I have 8 milligrams when it's 14 days, so I put 14 up here. And then this is just a number, so I'm going to go ahead and divide both sides by it to get A by itself. When you plug it into your calculator, you get approximately 90.51 milligrams. Okay, and so now let's just move on with our next part. Now that I know what A is, I can go ahead and plug it in, and that's my formula for this problem. Okay, so I just went ahead and put that in there. Now it says, what is the mass 6 weeks after the start? Now it's asking about 6 weeks, but X is being represented in number of days, so I have to do some unit conversions here. So 6 weeks means 42 days, right? Because there's 7 days in a week. So you do 7 times 6 to get the 42. So I'm going to plug 42 in for x. And then I'm going to use my calculator to solve. And I get 0.0625 milligrams of palladium 100 is left after 6 weeks. All right, so let's look at some logarithmic applications. Students will be able to solve applications using logarithms. Example 1, light intensity. The relationship between intensity I of light in lumens at a depth of x feet in Lake Superior is given by the log of I divided by 12 equals negative 0.0125 times x. What is the intensity at a depth of 10 feet? All right, so let's figure out what we're given. Besides the equation, of course, we're given the fact that x, the depth, is 10 feet. And we're asked to find I. So because we were given an equation, this is pretty simple. We don't have to think about how to put the equation together. We just have to know how to get I by itself. So I went ahead and replaced x with 10. And then just remember that if you don't see the base there like this, it's because there's a 10 there. It's log base 10. So I just went ahead and I used the exponential form in order to solve for this. So 10 to that power, which I took care of by multiplying by 10 already, equals I over 12. And then I multiply both sides by 12, and then I use my calculator to go ahead and give me the intensity. So I got about 8.999 lumens. Okay, let's look at another example, the Richter scale. The Richter scale magnitude R of an earthquake is based on the features of the associated seismic wave and is measured by the equation R equals log of A over T plus B, where A is the amplitude in micrometers, T is the period in seconds, and B accounts for the weakening of the seismic wave due to the distance from the epicenter. Find the period when the Richter scale magnitude of an earthquake is 6.35, the amplitude is 250 micrometers, and the B value is 4.25. Okay, again, we don't have to create the equation for this. It's given to us, which is really nice. We just need to know what we have and what we're trying to find. So what's given are all these values. The Richter scale magnitude is given, that's R. The amplitude, A, is given, and the B value is given. So that means we need to find the T value. So first things first, I'm just going to go ahead and substitute everything that I do know. based on the equation that was provided. And then I'm going to go ahead and move the 4.25 over to combine. And then remember, there's log base 10. Okay, so I put the 10 there. Now I'm going to translate this log equation into an exponential one. That's how I get rid of the log, or that's one way I can get rid of the log. So it's 10 to the power of 2.1 equals 250 over t. So in order to get t out of the denominator, I need to multiply both sides by t. And so I'm left with this equation. And then I need to divide both sides by 10 to the power of 2.1. And then plug into my calculator. And so I get about 2 seconds.